Hey everyone, welcome. We're jumping right into a really fundamental concept in physics today. We're looking at physical quantities, specifically scalars, vectors, and their units. You know, physics is basically the science of measurement. Every single claim we make, whether it's about the speed of light or the temperature of your coffee, it all comes down to a measurable quantity. But here's the catch. They don't all behave the same way. The difference between them is absolutely massive. If you mix them up, your calculations won't just be a little bit off, they'll be conceptually totally wrong. So let's dive right into it.
Okay, picture this. You step out your front door and walk exactly 5 kilometers. You know exactly how far you went, right? But if I ask, hey, did you make it to your friend's house? You can't actually answer me unless you tell me which way you walked. Does direction matter? Absolutely it does. And that simple question right there perfectly sets up the entire puzzle we're solving today. Some things can be totally described by just a number, while others literally need a direction to make any sense at all.
Section 1. Introduction to Physical Quantities. So, before we start sorting things into categories, let's nail down what we're actually looking at.
So what exactly is a physical quantity? Well, simply put, it's any property of a material or a system that can be measured and then expressed as a number with a unit. It really needs those two things. First, you got to be able to measure it in the real world. Second, it needs a unit. A number all by itself, pretty much meaningless without a scale. For instance, the mass of an apple is a physical quantity. You measure it, boom, you get an answer in kilograms. But something like the beauty of a sunset, not a physical quantity because you can't measure that in an objective, reproducible way.
Section 2. Scalars versus vectors explained. Now that we've got the basics down, let's divide these physical quantities into two broad families based on what information they need.
Let's start with scalars. A scalar quantity is completely described by its magnitude alone. And by magnitude, I just mean a numerical value plus a unit. That's the whole shebang. No direction needed whatsoever. The key test here is simple. If knowing how much gives you the whole story, it's a scalar, and they follow normal, everyday math. If you walk 3 kilometers and then another 2 kilometers, your total distance is just 5 kilometers. Direction doesn't matter one bit here.
Now, let's look at vectors. A vector quantity absolutely requires both a magnitude and a direction to be fully defined. If you just give one or the other, your description is totally incomplete. Think about force. If I tell you a force of 10 newtons is acting on a box, you still have no idea what's going to happen to that box. Is it being pushed to the right, upwards, at a weird angle? Knowing which way the force pushes is absolutely essential.
This visual really hits the nail on the head. On the left side, we've got a thermometer and a beaker. It says 25.0 degrees Celsius. That's magnitude only, a classic scalar. It'd be silly to say the temperature is 25 degrees north, right? But over on the right, look at that force gauge pulling the mechanical arm. It reads 150 newtons, but you see that arrow? It's pulling up and to the right at a 30-degree angle. Magnitude plus direction. That right there is a vector.
It's kind of fun to see all these familiar terms grouped up. Here's a lineup of common scalar quantities and their standard units. We've got mass in kilograms, speed in meters per second, distance in meters. There's also temperature, time, energy, power, and electric charge. Since direction doesn't apply to any of these, you can just add and subtract them like you learned in elementary school. 2 kilograms plus 3 kilograms is always, without fail, exactly 5 kilograms.
But wait, compare those to our common vector quantities. Things like displacement, velocity, acceleration, force, momentum, and weight. You can't just use regular arithmetic with these guys. You can't just add their numbers together, because their directions might actually cancel each other out. If you have two 5-newton forces pushing the exact same way, sure, they combine to 10 newtons. But if those exact same forces push in opposite directions, they completely cancel out, leaving 0 newtons. Same numbers, wildly different result.
Now, this brings us to something that trips up a lot of people. Take a look at speed and velocity. They both use the exact same unit, meters per second. So, how can the same unit describe both a scalar and a vector? Well, the unit just tells you the physical dimension. It doesn't tell you if direction is involved. That part depends entirely on how the quantity itself is defined. Speed is actually just the magnitude of velocity. The vector, velocity, cares about the direction, while the scalar, speed, just totally ignores it.
Section 3. Formulas and visual understanding. Knowing if something is a scalar or a vector actually changes how we use physics formulas in the real world. Let's see how.
Let's look at Newton's second law for a second. Force equals mass times acceleration, or F equals ma. Here, force and acceleration are vectors, but mass is just a scalar. Because of how this equation is set up, it literally dictates that the net force and the acceleration have to point in the exact same direction. If an object is accelerating to the right, the net force must be pointing to the right. It's permanently locked into the math.
Okay, now what about kinetic energy? The formula is Ke equals 1/2 mv squared. But hang on, velocity is a vector, right? So why in the world is kinetic energy a scalar? Well, it's because the formula squares the velocity. Whenever you square a vector's magnitude like that, it strips away the directional information entirely. You're just left with a scalar. That's why kinetic energy is always just a pure, positive number, no matter which way you're throwing the baseball.
And remember, adding vectors isn't as simple as just saying 2 plus 2 is 4. You have to factor in their angles. If they aren't parallel, you use rules like the parallelogram law. You literally map them out visually or use a bit of trig to find the new resultant vector. If you have two forces pulling at an angle to each other, they merge to create a brand new force that pulls diagonally between them. It's like a tug of war where both sides kind of win.
Section 4, Real-Life Vector Examples. Let's step out of the textbook and see how this stuff actually shapes the real world around us.
Let's talk about getting around, navigation. Say you walk from your house, stop at a market, and then finally get to your friend's house. That dotted line right there is the winding path you walked. Your total distance? 2 kilometers. That's a scalar. It's just the length of your path. But your displacement is that straight red arrow slicing directly from your home to your friend's house. That straight line vector is only 1.5 kilometers, pointing, say, 35 degrees north of east. Same exact trip, but totally different answers depending on if you want the scalar distance or the vector displacement.
Here's a really wild example from track and field. Imagine a sprinter running a 400-meter race around an oval track. They sprint their heart out, finish the lap, and stop exactly where they started. Now, their average speed is huge, just distance divided by time. But what about their average velocity? Well, because they ended up in the exact same spot they started, their total displacement is 0. So crazy as it sounds, their average velocity for the entire race is exactly 0. A coach cares about speed, but a physicist? They're looking at that 0 velocity.
Section 5, Common Mistakes and Recap. So mechanics can definitely be tricky, and it's easy to slip up here. Let's cover some common traps so you can dodge them on your next test.
First big mistake, treating vectors like scalars when adding them. If you've got a velocity of 3 meters per second and another of 4 meters per second, they do not automatically make 7 meters per second. If they're pointing at right angles to each other, the total is actually 5 meters per second, thanks to the Pythagorean theorem. Direction matters. Second mistake, thinking a negative sign means smaller. With vectors, a velocity of negative 5 meters per second is absolutely not slower than positive 3 meters per second. That minus sign just means it's going the opposite way. A speed of 5 is always faster than 3, no matter the direction.
So, quick recap. Scalars are all about magnitude, mass, temperature, speed, energy. Vectors bring magnitude times and direction to the party: force, velocity, displacement, momentum. The absolute biggest takeaway today? If you treat a vector like a scalar, your calculator might give you a nice, clean number, but physically, you'll be completely wrong. This one little distinction changes all the math.
Section 6, Practice Questions. All right, let's wrap this up with a quick pop quiz. These are pulled straight from the most common questions on this topic. Let's see what you've learned.
Question number 1. Take a second to think about this. Is temperature a scalar or a vector quantity? If you measure a room at 300 Kelvin, does that measurement need a direction to make sense?
Well, if you said scalar, you hit the nail right on the head. Temperature is purely a scalar quantity. It's got a magnitude, like 300 Kelvin, but absolutely zero directional component. You literally can't have a temperature pointing north, and the same goes for things like heat and internal energy. They are pure scalars, through and through.
Okay, let's end on a bit of a brain teaser. If an object is moving in a perfect circle at a perfectly constant speed, is its velocity changing? Keep in mind, speed is a scalar, so that's constant here. But velocity is a vector. It needs speed and direction. Because that object is curving around the circle, its direction is constantly changing at every single fraction of a second. And since the direction changes, its velocity is constantly changing too. Mind-blowing, right? That little concept actually sets up everything you'll learn about circular motion. Anyway, I hope this explainer made scalars and vectors crystal clear for you. Keep practicing, and I'll catch you in the next one.